Alright, today we'll be looking at the topic of particle dynamics and specifically collisions. And here's a sample problem. So, a neutron moving through heavy water strikes an isolated and stationary deuteron, which is the nucleus of an isotope of hydrogen, head-on in an elastic collision. Ready?
Bruh.
So, for part 1, it says, assuming the mass of the neutron is equal to half that of the deuteron, find the ratio of the final speed of the deuteron to the initial speed of the neutron. So we know that the neutron, which we can call Mn, is equal to 1/2 the mass of the deuteron, which we can call Md. So we can multiply both sides by 2, and we'll get 2Mn is equal to Md. So we can use the law of the conservation of momentum in this case. So we know that the mass of the neutron multiplied by the velocity of the neutron initially is equal to the mass of the neutron multiplied by the velocity of the neutron after the collision, which we can call Vn prime, added to the mass of the deuteron multiplied by the velocity of the deuteron after the collision, which is Vd prime. So because we know that 2Mn is equal to Md, we can substitute that into this equation. So we know that Mn Vn is equal to Mn Vn prime plus 2Mn Vd prime. So we can divide both sides by Mn. So we get Vn equals Vn prime plus 2Vd prime. Now we can call that equation 1. So we're looking at the ratio between the final speed of the deuteron to the initial speed of the neutron. So we're looking for the ratio of Vd prime to Vn. So let's isolate for Vn prime. So we know that Vn prime is equal to Vn minus 2Vd prime. That's our equation 1. So we also know that kinetic energy is conserved in the entire system at the beginning and at the end. Alright, so we know that kinetic energy is conserved. So 1/2 Mn Vn squared is equal to 1/2 Mn Vn prime squared plus 1/2 Md Vd prime squared. So now we can substitute 2Mn equals Md into this equation as well. So we get 1/2 Mn Vn squared is equal to 1/2 Mn Vn prime squared plus 1/2 multiplied by 2Mn multiplied by Vd prime squared. So we know that 1/2 Mn Vn squared is equal to 1/2 Mn Vn prime squared plus Mn Vd prime squared. So we can also divide both sides by Mn. So we get that 1/2 Vn squared is equal to 1/2 Vn prime squared plus Vd prime squared. So let's multiply both sides by 2. We get Vn squared is equal to Vn prime squared plus 2Vd prime squared. Alright, so we know that Vn squared is equal to Vn minus 2Vd prime all squared plus 2Vd prime squared. So now we can simplify that. So that's Vn squared is equal to Vn squared minus 4Vn Vd prime plus 4Vd prime squared plus 2Vd prime squared. So we can subtract Vn squared from both sides, and what we end up getting is 4Vn Vd prime is equal to 6Vd prime squared. So we divide both sides by Vd prime. So we get 4Vn is equal to 6Vd prime. And we can set up a ratio, so we know that 4/6 is equal to Vd prime over Vn. So we know the ratio between the final speed of Vd prime and Vn is 2 to 3. Alright, now we can move on to part 2. So the question asks, what percentage of the initial kinetic energy is transferred to the deuteron? So for this we can use 1/2 mv squared. So 1/2 mn Vn squared. And basically we're looking for the ratio between the initial kinetic energy and the kinetic energy of the deuteron at the end. So put that to the ratio of 1/2 md Vd prime squared. So now we know exactly what md is and what Vd prime is. Using these equations we derived earlier, we can substitute that in. So 1/2 mn Vn squared to 1/2 2mn 2/3 Vn all squared. So that's equal to 1/2 mn Vn squared to mn 4/9 Vn squared. Now we can divide both sides by mn. We can also divide both sides by Vn squared. So we get 1/2 to 4/9, and that's equivalent to 1 to 8/9. So now we know the ratio between the initial kinetic energy and the kinetic energy of the deuteron after the collision is 1 to 8/9. So that's 100% to 88.9%, which is essentially equivalent to 89%. So we know that 89% of the initial kinetic energy of the neutron is transferred to the deuteron. Alright, so part 3 asks, how many such collisions would be needed to slow the neutron down from 10 mega electron volts to 0.01 electron volts? So we've gotten from here that the deuteron receives 89% of kinetic energy, which means that if the total is 1 at the beginning, the neutron gets 1/9. So every time the collision occurs, the neutron energy is divided by 9. So essentially, we can set up an equation that looks like this. So 10 mega electron volts, so that would be 10 to the power of 7 electron volts multiplied by 1/9 to the power of n equals 10 to the negative 2 electron volts. So we can divide both sides by electron volts, and we can move this 10 to the other side. So we get 1/9 to the n is equal to 10 to the negative 9. So now we know that the log with base 1/9 of 10 to the power of negative 9 is equal to n. So we get n is approximately equal to 9.6. Because we cannot do the collision 9.6 times. We round it up to the nearest integer value that's above it. So we know that n is equal to 10. So after 10 collisions, the energy of 10 mega electron volts would be 0.01 electron volts. So part 1 says, assuming the mass of the neutron... No! Again. So 1/2 mn Vn squared is equal to 1/2 mn Vn prime squared plus 1/2 m. So now that we have equation 2 and equation 1, we can put equation 2 and substitute that into... Messed up. Don't worry about it. D prime all squared. Shoot. No, it's not all squared. Vn squared is equal to Vn. I don't even know what equation 1 is. God damn it. Oh my God.